Hi, today we'll be presenting our final project for cloud security. First, Aidan will look at Azure App Service, focusing on how managed platforms simplify deployment and security. Next, I will compare this with a VM-based web server deployment, demonstrating how subnets, NAT, and layered security are used to enforce isolation and traffic control. Finally, Daniel will wrap up with logging and alerting, showing how logging detection and automated alerts support real-world incident response in a cloud environment.
Hi everyone. We thought one of our highlights from our labs was our custom written web application from Chapter 6. We thought it was a highlight because it shows how effective cloud infrastructure can be for shifting much of the infrastructure security to the cloud provider, which reduces the amount of configuration required for the customer and improves convenience. It also helps reduce common misconfiguration errors, which are a major cause of real-world breaches. Customers remain responsible for application level security, while the platform security is handled by the provider. This is still a trade-off, and you give up some direct control in exchange for professionally managed security. So here you can see we used Azure Web App Services to deploy our small Python Flask application. And it has a valid TLS cert issued from the Azure Cloud Certificate Authority that should be trusted by default on most client machines. And this was one of the lessons learned, though. We found we couldn't create a certificate with a custom hostname in the cert subject because the free tier didn't allow it using the app service certificate page. For administration, we were able to completely disable SSH access and still make code changes by Azure automation that triggers when you make a git commit and push that change to a remote Git repo stored in the cloud. So this is what it looks like to deploy using Git triggers. And this is what allowed us to disable SSH completely. So we can make a code change here and have that code change replicate, or have that code change be pushed out. And I'll fast forward through this to show what it looks like. We even went a step further and thought of a use case where an administrator might want to change the image that appears in the web app, because that would be a common task that shouldn't need a code change. We thought it was really cool that you can set the environment variables directly in Azure App Services without having to interact with the underlying Linux OS. And you can also see we extended this functionality for more important things like vault secrets. And it's important to note that the vault secret here is not the actual value, just a pointer to um, a URI, where the secret is securely stored somewhere else in the cloud. And now we can see our code changes have taken effect in the production. And it's nice that neither action requires to restart the web app, so there is zero downtime. We were also able to perform dependency scanning on our web application using both pip audit and SNCC within the Azure Cloud Shell. Pip audit was easy to install via the Python package manager, and it initially identified a security issue with Jinja 2, that was one of our dependencies. There was no SNCC integration directly in the Azure Marketplace, but we created a free account which provided us with an API token, and using that token we could connect the SNCC CLI within the Azure Cloud Shell, and successfully connected it to our Python web application. For us, SNCC scanned 9 dependencies and found no vulnerabilities. Thank you all for listening.
For this lab, we built a secure segmented cloud for our virtual machine-based web server deployment. Unlike Azure App Service, for this model, the customer is fully responsible for securing both the platform and application layers. This requires manually designing and securing the network, routing, and traffic controls. The environment is split into 2 subnets within a single virtual network: a public subnet for internet-facing systems and a private subnet for internal resources that must never be directly exposed. A NAT virtual machine in the public subnet is configured with IP forwarding and IP tables to allow outbound internet access for updates while blocking unsolicited inbound traffic, forcing all private subnet traffic through a single controlled exit point. A private database VM runs in the private subnet with no public IP and is accessed only by first connecting through the NAT VM. A public-facing web VM with a public IP is configured as a reverse proxy, securely forwarding requests to the private VM using its internal IP. NSGs are tightly controlled to allow only ports 80 and 443 to the public VM. Subnet-based VM deployments offer maximum control but require careful manual security configuration, while Azure App Service shifts much of this responsibility to the provider and pre-configures allowed ports. Subnet deployment also allows NSG-based traffic filtering for explicit network isolation and controlled routing, whereas App Service only supports this at higher service tiers. Unlike Azure App Service, every allowed port in this model must be manually defined. For inbound traffic, we only allow HTTP and HTTPS to the public web server, and SSH is restricted to a single admin IP for secure management. The allow internet rule permits the private subnet to reach the internet through the net VM. The remaining rules are the default NSG settings. Internal VNet and Azure load balancer traffic are allowed, and all other traffic is denied by default. The outbound rules are currently using the default NSG settings allowing VNet and internet traffic. They're left open for this lab, but in production they'd be restricted to only the specific connections required. Unlike App Service, outbound traffic here is manually forced through a NAT VM, which is the only internet-facing exit point for the private subnet. As shown in this trace route, traffic from a private machine to example.com first hops through the NAT VM. Here you can see that the private VM has no public IP, so it's not directly reachable from the internet. All access must pass through the NAT and reverse proxy. And with that, I'll hand over to Daniel, who will now walk us through logging detection and automated response in the cloud.
As we've seen throughout the course, when it comes to the cloud, security without visibility is just wishful thinking, and visibility without response is just noise. Attackers thrive in environments with little to no visibility, and they can quickly conduct malicious actions before human defenders can react. Because of this, cloud environments require comprehensive logging, often extending beyond system default settings. Thankfully, Azure provides a variety of mechanisms to collect and analyze audit logs. Azure Monitor collects logs for the environment at the subscription level. This allows us to view all the activity performed on the subscription and ties it to the identity of the users that perform the actions. These results can be filtered by severity level and the time span adjusted to only show events that occurred during a given period. This is an important feature that allows security personnel to search for events that occurred during an incident, and the ability to tie events to identities allows administrators to take actions like disabling accounts or revoking and rotating credentials. Another key feature in Azure which allows us to centralize and analyze logs from our various resources is Analytics Workspaces. Within our environment, we created an Analytics Workspace and configured our resources to send diagnostic logs to the workspace, which allowed us to not only view the logs, but perform queries on the logs. For example, we could view key creation and deletion events that occurred on our Azure Key Vault. It's important to note that Analytics Workspaces are not enabled by default and must be created and configured to ingest logs from Azure resources. By enabling this feature, we ensure that we don't have blind spots in our environment that could potentially be exploited by attackers. Yet another service offered by Azure is Microsoft Defender for Cloud, a cloud-native application protection platform. This provides a wide range of security functionality, but like log analytics, it must be enabled. After being enabled, Defender can not only provide alerts, but also provide security recommendations to improve the posture of the environment. Here we can see various sample alerts that we generated that show a variety of VM-centric alerts that are organized by their severity. Defender even ties events to MITRE attack tactics, techniques, and procedures. As I mentioned before, knowing that something is happening doesn't do us much good if we can't respond to it. So we implemented a logic app that is triggered by Defender alerts. When a Defender alert is fired, two actions are taken. The first is that an email is sent to relevant security personnel, in this case, Anna, Aiden, and myself. The second is that tags for the virtual machine in question are updated. A tag is added that states review resource. This is a very simple example of automation, but logic apps and some premium features of Defender allow for much more robust security automation. Thank you.